Hello everyone, myself Kirtana R from Sri Venkateshwara College of Engineering. As you can see on the screen, my topic is identifying networks vulnerable to IP spoofing. The agenda for today is introduction, proposed system which contains varying announcement location, varying the AS path length with BGP, announcement configuration and measuring the catchments. Firstly, let us know what is an IP spoofing. Hackers can hide their identities by changing the source IP address of their internet traffic using a technique called as IP spoofing. So here, IP spoofing is a technique used by the hackers to disguise their identity by altering the source IP address of their internet traffic. In this technique, the attacker modifies the IP address in the packet headers of their data to make it appear that the traffic is coming from a different source rather than the attacker's actual IP address. By altering the IP address in the packet headers of their data, the attacker can make it appear that the traffic is coming from a different source rather than their own IP address. IP spoofing is frequently used in denial of service attacks, in which attackers flood a target system with traffic to overwhelm it and prevent legitimate users from accessing it. By spoofing the source IP address of the traffic, the attacker can make it difficult for the target systems to filter out the malicious attack. The attacker might make it challenging for the target system to block malicious traffic by forging the source IP address of the traffic. Man-in-the-middle attacks and session hijacking are two further attack techniques that utilize IP spoofing. However, IP spoofing alone is not enough to successfully carry out these attacks, as the attacker also needs to be able to intercept and manipulate the traffic in transit. The attacker must also be able to intercept and modify traffic in transit, therefore IP spoofing alone is insufficient to carry out these attacks. Internet protocol spoofing is a form of malicious attack in which the threat actor conceals the real IP packet source in order to make it harder to determine where the packets are originated. Attackers may find IP spoofing to be a strong tool, but it also has certain drawbacks. To stop IP spoof attacks, for instance, many modern network includes security techniques like ingress and egress filtering. In addition, some protocols like TCP have features that can aid, detect, and prevent IP spoofing. TCP packets carry sequence numbers used to allow out-of-order stream data to be reassembled in order and to track what data has been received so far in each side of a stream, and if necessary, signal retransmissions of stream data assumed to have been lost. The TCP protocol specification requires that each site set a random initial sequence number during the connection opening handshake. However, some implementations have been quite a bit less random than others. If an attacker can open one TCP stream to a target host, then have a good chance of predicting what sequence number might be used in a subsequent connection to the host from another location. The attacker can create a forged TCP packet appearing to be from the other location with sequence numbers that might be accepted by the target host, inserting data stream into a stream belonging to someone else. This can give an attacker some chance of inserting data into some other active session. However, inserting the right data into a security-sensitive session can be dangerous or disastrous. TCP implementations have sometimes beefed up the methods they use for generating initial sequence numbers, preferably a cryptographic pseudo-random number generator. Another defense against TCP spoofing is the use of encrypted protocols like SSH and SSL or TSL. Encryption of the TCP stream data makes it harder to insert arbitrary data into sessions, since the attacker would also have to determine the encryption methods and keys in use. However, the successful insertion of random data into an encrypted session can cause denial of service if one endpoint detects the invalid data and decides to abort the session. Here we have the normal interaction. We have the source IP address, which is the IP packet field containing the IP address of the workstation from which it came, and the destination IP address, which is the IP packet field containing the IP address of the workstation to which it is addressed. Each IP datagram contains a source address and a destination address. Based on the IP addresses in the packet header, there is a task of delivering packets in IP from the host to the destination host. Whatever is the encapsulated data that has to be delivered is defined by the IP packet structure. With source and destination information, it defines addressing methods that are used to label the datagram. Here we have the interaction under spoofing. Internet traffic is sent in units referred to as packets. As I told, packets contain IP headers that have routing information about the packet, that is the source IP address and the destination IP address. Think of the packet as a package in the mail and the source IP address as the written address on that package. In IP address spoofing, the attacker changes the source address in the outgoing packet header. That way, the destination computer sees the packet as coming from a trusted source, such as a computer on an enterprise network, and accepts it. Attackers may generate fraudulent packet headers by falsifying and continuously randomizing the source address using a tool. They may also use the IP address of another existing device so that the responses to be spoofed packet go there instead. To carry out IP spoofing, attackers also need a trusted IP address that the receiving device would permit to enter the network. There are numerous ways to find device IPs. One way is Shodan, an online database of IP address to manage device mappings. And the ability to intercept the packet and swap out the real IP header for the fraudulent one. A network sniffing tool is another tool which is used for this. Here are the proposed systems. Firstly, varying announcement location. Prefix announcement from multiple peering links enhances route diversity and on average results in smaller catchments. This could refer to changing the location information in the IP packet's header to make it appear as if the packet is originated from the different location. Smaller catchments help localize fake traffics more accurately. This could mean altering the IP packet's header's location information to make it appear as though the packet is coming from a different location. There are several ways in which an attacker could vary the announcement location in IP spoofing. One way is to use a proxy server or botnet that is located in the different geographic location than the attacker. By routing the spoofed IP packets through these intermediate servers, the attacker can make it appear as if the packets are originating from the different location. An attacker could change the announcement location in IP spoofing in a number of different ways, using a proxy server or the botnet that is situation where somewhere else than where the attacker is can. Next we have varying the AS path length with BGP. Where there are multiple routes with the same local prefix available, which can be used by a network operator to influence the path choice of other autonomous systems, BGP prepending lengthens the path relative to most other paths in the internet by repeatedly appending the network operators as number to the start of the AS path attribute of their BGP announcement, which can be used by a network operator to influence the path selection of other autonomous networks, which when there are multiple routes with the same local prefix to be chosen from. BGP prepending involves adding the network operators as number multiple times to the beginning of the AS path attribute of their BGP announcements, which makes the path longer than most other paths in the internet. Next we have the announcement configuration, wherein a network operator can inform other autonomous systems on the network of the routing details for the network prefixes. An internet network operator can decide whether to announce their prefixes to one or more transit providers as well as their peers and customers when using the Border Gateway Protocol, that is BGP, which is used for inter-domain routing. in which a network operator can announce the routing information for their network prefixes to other autonomous systems on the network. The broader gateway protocol, that is BGP, which is used for the inter-domain routing on the internet. A network operator can be chosen to announce their prefixes to one or more transit providers as well as to their peers and customers. In the context of internet routing, determining the areas or regions where internet traffic is coming from and going is known as measuring catchments. Because the prefixes they are monitoring do not carry any production traffic, the researchers in this case can enable to passively observe traffic in infer catchments. So they use a combination of BGP updates and trace routes to measure these catchments. Catchments measurement has no production traffic for peering prefixes, so we cannot passively observe traffic to determine the catchments. Next, we have measuring catchments. In the context of internet routing, determining the areas or regions where the internet traffic is coming from and going to is known as measuring catchments. Because the prefixes they are monitoring do not carry any production traffic, the researchers in this case are unable to passively observe traffic to infer catchments, so they use a combination of BGP updates and trace routes to measure catchments. In this particular case, the researchers cannot passively observe traffic to infer catchments because the prefixes they are monitoring carry no production traffic. So they use a combination of BGP updates and trace routes to measure catchments. Measuring catchments, peering prefixes carry no production traffic, so we cannot passively observe traffic to infer the catchments. Catchments measurement has no production traffic and we cannot passively observe traffic to determine these catchments. Now let's come to the conclusion. Control plane traceback technique can be used by any network with a lot of connections today without needing to change their routers or get help from other networks. We found that this technique works well to figure out where fake or harmful internet traffic is coming from, even if there are only a few places generating the bad traffic. These technique can group these sources of bad traffic into sets of around 1.29 networks called autonomous systems. If larger networks are used, then this technique will be even more accurate. This can also be used to make the internet safer and more reliable. Today, any network with extensive connectivity can implement our control plane traceback method without modifying routers and without the assistance of other networks. Our findings on the peering platform show that the techniques we have suggested for creating announcement configurations can successfully alter routes and cause catchment changes, enabling the identification of the origins of spoofed traffic. Our techniques can map sources of spoofed traffic into sets that average the autonomous networks if sources of amplification and DOS attacks are few, as shown by the log analysis from the AMPOT honeypots. Our findings suggest that if networks with a footprint larger than piercings implement our techniques, precision will be higher. For upcoming research, we see two avenues. One is to broaden our network to even further so that we can reduce the cluster sizes. Here we have the references. Thank you for watching my video. Don't forget to like and comment.